So now I'm jumping into section 14.6 next here, as you can see. I'm not skipping 14.5. I just kind of do things in a certain order that I like. So you get used to that. You might see me like jump over one section and then circle back around to that section. Okay. So 14.6, heterogeneous equilibrium. So up to now, the only examples that I've given you are all the same phase, and they've predominantly all been gas phase reactions. But when we look at heterogeneous equilibrium, that's chemical equilibrium involving more than one phase. Okay, so for example, this reaction here, 2H2O liquid reacting to form 2H2 plus O2. Now, this is kind of a ridiculous example because if you followed along from my previous example, we talked about how water is just not going to fall apart unless we like do something to it. If there's another reactant here that's missing. But all the same, this serves as a good example. Okay, and here I'm showing you two different equilibrium expressions for this reaction. Okay, so this first one, let's check it out. We've got H2 squared times O2 divided by H2O squared. And then now I've also written H2 squared just times O2, but I don't have the H2O anymore. Well, as it turns out, this one is not correct. And this one is correct. So why is that? Well, let's look at the phases. So in this reaction, this is specifically liquid water reacting to form gas phase hydrogen and gas phase oxygen. So if you think about this, if you think about the concentration of a pure liquid or the concentration of a pure solid, you can never change its concentration. So let's think about this for the example of a pure solid. Okay, so let's suppose we've got our like little salt crystal or something like that. We're going to eventually talk about solids, but suppose, let's just say we've got a little, cubic shaped salt crystal. Okay, well now if some of this goes and reacts, hopefully I can draw this, right? There's going to be like a little missing chunk, right? Hopefully my drawing kind of makes sense what I'm trying to draw right there, right? There's like a little bite that's been taken out of it, okay? Well, so if you think about this, that means for that pure solid, its mass has been reduced, but also its volume has been reduced. So it actually has not changed in concentration, okay? So if pure solids or pure liquids are involved in a reaction, their concentrations are not included in the equilibrium expression because you can't change the concentration of a pure liquid or a pure solid. You can change the concentration of a gas, however, because if you remember this from Chem 109, a gas will spread out and fill the available volume that it has. However, if you've got gas confined to a fixed volume and you start reacting some of those gases away, the volume stays fixed, right? So if the volume stays fixed and the mass decreases or increases, then you can change the concentration of a gas, okay? So once again, if pure solids or pure liquids are involved in a reaction, their concentrations are not included in the equilibrium expression. Okay, well, what about aqueous stuff, right? So in reactions involving aqueous species, their concentrations are included in the equilibrium expression because now, once again, if we think about something that's aqueous, it is a certain number of moles of solute dissolved in a certain number of liters of solution. Well, the liters of that solution will remain fixed if the aqueous species is reacting away, okay? So aqueous and gas phase are always included. So in a reaction involving gas phase species, their concentrations are included in the equilibrium expression, okay? So once again, when we look at this reaction, we can see that water here is given as a liquid, so we do not include it. If this was gas phase water, then we would include it, okay? So let's do a couple examples. So write the law of mass action or equilibrium expression for the following three reactions. And admittedly, some of these are going to look kind of goofy because, for one, this very first example, right, with CaO3 reacting to form CaO and CO2, notice that we've got a solid, and a gas. So that means our Kc for this equilibrium reaction is just simply the CO2 concentration. And of course, this would be expressed unitless, but all the same, we don't have to worry about the concentration of these other reactants and products, okay? So what about this next reaction? Well, we've got a solid, we've got a liquid, and we've got a gas. So once again, my Kc for this reaction is just going to be simply Cl2, all right? So now these first two examples we did are kind of like weird, and we won't encounter stuff like that very much, but we will encounter this kind of situation a lot, okay? So we've aqueous HCl plus H2O liquid to make H3O plus aqueous plus Cl minus aqueous, okay? And so we need to include all of those aqueous species in the equilibrium expression. So now that's going to be H3O plus times Cl minus, I didn't like the way that turned out very well. Let's do that again. Okay. Times Cl minus, all divided by HCl. So we're not including the water because it's listed as a pure liquid, but we do include all of the aqueous species. So this is what we're going to see quite a bit in this class because we will routinely deal with aqueous reactions.